As in example 8.1.2, the congruence modulo 2 relation E is defined from Z to Z as follows. For every ordered pair M, N in Z cross Z, M is related to N if and only if M minus N is even. Part A is 0 related to 0. Now, it says here 0E0, but E is a relation. It says right here, relation E. What that means is that when we write that letter capital E, we're really saying that these two elements, 0 and 0, are related under the relation E. So this says, is 0 related to 0? And I'll type that out here. Under the relation E. Now we're going to use this if and only if statement as our framework here. M is 0. That's the first element. N is 0. So we're saying M equals 0 and N equals 0. Now this is true. 0 is related to 0 if and only if 0 minus 0 is even. And so when we ask ourselves, is 0 related to 0 under relation E? What we're really asking is 0 minus 0 even? That's the same question. Now, 0 minus 0 is 0, and 0 is even. However, in this class, we have to demonstrate that it's even, meaning we have to write this number as 2 times some integer. So I'm going to rewrite this 0 as 2 times 0. 2 times 0 is also 0, but this implies that 0 is even though that's kind of obvious. Here we have made that justification to avoid circular reasoning. Is 5 related to 2? Well, that's really asking the question, is 5 minus 2 even? So is 5e2, is 5 related to 2? Is 5 minus 2 even? All of those mean the same thing. Now, to show that this is not even, I'm actually going to show that this is an odd number. This is 2 times 1 plus 1. So that's an odd number. So that means the answer to this question is no. Whereas the answer to the question in the beginning of part A was yes. So 0 is related to 0. Yes, that's true. 5 is related to 2. No, that's not true. And then now let's move on to the next part of this question. 6, 6, the ordered pair, is an element of E. Notice how this says something very different than the first two parts of this question. This is an ordered pair, 6, 6, which is an element of a set. In this case, E is being treated as a set, whereas in the other case, 0E0 and 5E2, we say 0 is related to 0 and 5 is related to 2. It's a very different notation. So in this context, E is a set of ordered pairs that contain all of the elements that are related to each other under that relation. So when they're asking us, is 6, 6 an element of E, they really mean, is 6 related to 6? This is just a fancy way of asking this question. And we know, based on the previous two questions, we kind of already know what that looks like. That's really asking, is 6 minus 6 even? That's a much easier question to answer. 6 minus 6 is 0, which is 2 times 0. And so that's an even number. And so the answer to this question is yes. Yes, the ordered pair, which, let me scroll up here. The ordered pair is an element of Z cross Z. Z cross Z is the set of all ordered pairs where the first element and the second element are both integers. This is the lattice, put it another way. But the relation E is defined from Z to Z as follows. For every ordered pair, M, N, in the set Z cross Z, that's a set of ordered pairs. So this is just a different notation, but it really just means the same thing. Is 6 related to 6? And the answer is yes. And lastly, we have, for part A, is negative 1 comma 7 in E? That's the same thing as asking, is negative 1 related to 7 under the relation E? And that's the same question as, is negative 1 minus 7 even? And this is the question that we're really focusing on. Negative 1 minus 7 is negative 8. And negative 8, more importantly, is 2 times negative 4. So this is an even number. And so the answer to this question is yes. That's part A. So this is just practice with all of the notations for relations. Part B, prove that for any even integer n, n is related to 0 under the relation E. Okay, so let's prove that. Okay, the proof is, we're going to start with our assumptions. Let n be an even integer. We have to prove that for any even integer n is related to 0. So we're starting with an arbitrary n that's an even integer. And we're going to show that even though n is arbitrary, n could be any even integer, it doesn't matter what that even integer is, n will still be related to 0. And that's what we're going to prove. So our goal here, and I'll put this, I like to, for all these problems, I like to write the goal, which is the conclusion. The conclusion that we're trying to get is that n is related to 0 under the relation E. Now I'm going to bring down this goal because we have to fill the gap between our assumption and the goal. Now, n is an even integer. We know what that means. We know the definition of an even integer is that n equals 2k for some integer k. That's the definition of even. We need to show that n is related to 0. Now, I think a lot of students might get stuck here. I think that's perfectly normal. A really common strategy I have for all of my videos, for all of my proofs, is what's called working backwards from your conclusion, which is where we take our goal and we unpack what that means. So in order to prove that n is related to 0 under this relation, we must first prove that n minus 0 is even. So that has to be the line before the conclusion. That's the only way we can justify this conclusion. By the definition of relation, n is related to 0 if and only if, according to this definition, if and only if m minus n minus 0 in this case, we're using m equals n, and n equals 0. I know that's a little weird because we're kind of reusing letters here. In the definition, in both the definition and part B, this n is not the same as that n. Just keep that in mind. These have very different localities to them. So we need to show that n minus 0 is even in order to justify that n is related to 0. So that's why we have a new goal that's much easier to attain. Why is n minus 0 even? Well, we know that n is even, but we have to justify why n minus 0 is even. Now, this is going to be a little bit of a weird step, and I feel like it might be a little uncomfortable for a lot of you, but I'm going to take this equation, and I'm going to subtract 0 on both sides. So this will be n minus 0, and I'll put here then. N minus 0 is 2k minus 0, which is 2k, and that's an even number. So now we've obtained this goal that n minus 0 is even, and so I'll replace that word goal with the word then. That's the next line of this proof. And then the conclusion immediately follows by design, since we worked backwards from the conclusion earlier. So this is the proof. Thanks, everyone.